Welcome to Senior High School Math Series. Let us have rational equations and inequalities under General Mathematics. This is Quarter 1, Week 2, based on Curriculum Implementation and Learning Management Matrix for K-12's most essential learning competencies. Here are our lesson objectives: to solve rational equations, to solve rational inequalities, and to solve word problems involving rational equations or inequalities. Before we continue, let us ponder on this. Education is the most powerful weapon which you can use to change the world, by Nelson Mandela. Okay, let us proceed to solving rational equation. Let us have some steps in solving rational equation. First, eliminate denominators by multiplying each term of the equation by the least common denominator. Next, note that eliminating denominators may introduce extraneous solutions, so do not forget to check the solutions of the transformed equation with the original equation. Let us have some examples. Number 1, solve for the value of x in the equation 2 over x minus 3 over 2x equals 1 over 5. So, following the steps in solving rational equation, we are going to eliminate the denominators by multiplying all terms by the LCD, or the least common denominator. This time we have x, 2x, and 5. So the LCD is 10x. So we're going to multiply all terms of this equation by 10x. So 10x times 2 over x minus 3 over 2x. On the other side, 1/5 times 10x. On the first term, 2 over x cancels, so that will be 10 times 2, 20. On the second term, 10x over 2x is 5, so that will be 5 times negative 3, so negative 15. Then we have 20 minus 15 on the left, and on the right side we have 5 and 10 can be divided by 5, so we have 2x times 1, so we have 2x. Then rewriting this equation, we have 2x equals 5, and then dividing both terms by 2, then we get x equals 5 over 2. Okay, let us check our solution. By checking, we are going to substitute the value for x 5/2 to all the x's in the original equation. So that will be 2 over 5/2 minus 3 over 2 times 5/2 equals 1/5. Remember that in checking the solution, we do not use transposing, or we do not use addition property of equality. We solve each side until we get equal values on both sides of the equality. So we have 2 over 5/2, that will be 2 times the reciprocal of 5/2, and that is 2/5. So we have 4/5. And then on the second term, 2 cancels, that will be 3/5. And then on the right side, it's 1/5. Now we have similar fractions, 4/5 minus 3/5. That will be 1/5 equal to 1/5. And the solution is correct. Next, let us have example number 2. Solve the rational equation 2 over x minus 10 plus 3 over x minus 2 equals 6 over x squared minus 12x plus 20. So from the equation, we can factor the denominator on the right side. Then we will have x minus 10 times x minus 2 in the denominator. Notice that our LCD is x minus 10 times x minus 2. So we're going to multiply all terms by this to get rid of the denominator. In the first term on the left, x minus 10 cancels, so that will be 2 times x minus 2. On the second term, x minus 2 cancels, so we will have 3 times x minus 10. While on the right, the denominator cancels, so we will just have 6 in the right side of the equation. Then by distributive property, we have 2x minus 4 plus 3x minus 30 equals 6. Let us combine similar terms. That will be 2x plus 3x, 5x. And then negative 4 minus 30, that's negative 4. So we add 34 to both sides. That will be 5x equals 40. And then divide both sides by 5, we get x equals 8. Let us check this solution. Substitute 8 to all the x's in the original equation. So we have 2 over 8 minus 10. Notice how 8 is substituted to all the x's. Plus 3 over 8 minus 2 equals 6 over 8 squared minus 12 times 8 plus 20. Let us resolve the denominators. So we have 2 over negative 2 plus 3 over 6 equals 6 over 64 minus 96 plus 20. Next, negative 1 plus 1 half equals negative 6 over 12. So negative 1 plus 1 half is negative 1 half, and negative 6 over 12 is negative 1 half. Therefore, our answer is correct. Next, example number 3. Solve the rational equation x over x plus 2 minus 1 over x minus 2 equals 8 over x squared minus 4. Factor the denominator in the right hand side of the equation. We'll have 8 over x plus 2 times x minus 2 in the right hand side. So our LCD to get rid of the denominators is x plus 2 times x minus 2. Then we have x times x minus 2 minus 1 times x plus 2, because x minus 2 cancels. In the right hand side, all the denominator cancels. We will have 8. By distributive property, we have x squared minus 2x minus x minus 2. And rewrite the equation. We have x squared minus 3x. Subtract 8 from both sides, so we have minus 10. Then by factoring, we have x minus 5 times x plus 2. So from here, we equate both factors to 0. X minus 5 equals 0, and x plus 2 equals 0. Then x equals 5, or x equals negative 2. Notice that negative 2 will make a term in the original equation undefined, so we exclude negative 2 in the solution. We'll only have x equals 5 in the solution for this rational equation. Let us check the answer. Substitute 5 to all the x's in the original equation. We have 5 over 5 plus 2 minus 1 over 5 minus 2 equals 8 over 5 squared minus 4. Then we have 5 over 7 minus 1/3 equals 21. That's 25 minus 4. Then subtract the dissimilar fractions on the left hand side of the equation. That will be LCD is 21. Then we have 15 minus 7. So that is 8 over 21. Then the answer is correct. Okay, let's proceed to another example. Example number 4. This time, let us have a word problem. The product of the reciprocals of two positive consecutive integers is 1 over 72. Find the two integers. So let x be the first integer, since we have consecutive integers, x plus 1 be the second integer. Then we have the equation 1 over x, the reciprocal of x, times 1 over x plus 1, reciprocal of x plus 1, equal to 1 over 72. Again, let us multiply this by the LCD, which is 72 times x plus 1. So in the first factor, x cancels, we'll have 72 times x plus 1, cancel also, so we have 72. On the right hand side, we have x times x plus 1, or x squared plus x. Then we write this equation into a quadratic equation. That will be x squared plus x minus 72. And by factoring, that is x plus 9 times x minus 8 equals 0. So equate each factor to 0. We have x plus 9 equals 0, or x minus 8 equals 0. So we have x equals negative 9. We exclude negative 9 in the solution set because we are looking for positive consecutive integers. Then we will accept x equals 8. Therefore, the two integers are 8 and 9. Question number 5. The speed of train A is 12 kilometers per hour less than the speed of train B. Train A travels 230 kilometers in the same time it takes train B to travel 290 kilometers. Find the speed of each train. So let x be the speed of train B, as the speed of train A is compared to that of train B, and then x minus 12 be the speed of train A, because the problem says train A is 12 kilometers per hour less than the speed of train B. And then let us approach this problem by using a table of the given. We have speed, time, and distance in columns, and then we have train A and train B in rows. So the speed of train B is x, and the speed of train A is x minus 12. Distance traveled, according to the problem, 230 kilometers for train A, 290 kilometers for train B. So if we solve for the time, that is distance over speed, that will be 230 over x minus 12 for train A and 290 over x for train B. In the problem, it says train A travels 230 kilometers in the same time it takes train B to travel 290 kilometers. Therefore, the times are equal. 230 over x minus 12 equals 290 over x. Okay, multiply this rational equation by LCD. We have 230 times x equals 290 times x minus 12. Distributive property. Distribute 290. We have 290 times x and 290 times negative 12. That is 290x minus 3,480. Then 3,480 subtracting 230x from both sides is 290x minus 230. Then we have 3,480 equals 60x. Divide both sides by 60, we get x equals 58. This is the speed of train B. For train A, we have 58 minus 12. Therefore, train B travels 58 kilometers per hour and train A travels 46 kilometers per hour. Proceed to the next, solving rational inequality. To solve rational inequality, we follow the following steps. First, we rewrite the inequality as a single rational expression on one side of the inequality symbol and 0 on the other side. Next, determine over what intervals the rational expression takes on positive and negative values. And how do we do that? Locate the x values for which the rational expression is 0 or undefined. A useful strategy is to factor the numerator and denominator of the rational expression. Next, mark the numbers found in the first. On a number line, use shaded circle to indicate that the value is included in the solution set, and a hollow circle to indicate that the value is excluded. This number partition the number line into intervals. Next, select a test point within the interior of each interval into. The sign of the rational expression at this test point is also the sign of the rational expression at each interior point in the aforementioned interval. And finally, summarize the intervals containing the solutions. Okay, let us apply the rules in solving the examples. Number 1, solve for the value of x in the inequality 2x over x plus 1 is greater than or equal to 1. So following the rule, we subtract 1 from both sides of the inequality so that the right-hand side will be 0. Then we have 2x over x plus 1 minus 1 is greater than or equal to 0. And then rewrite the left-hand side as a single rational expression. LCD is x plus 1. Then we will have 2x minus quantity x plus 1 all over x plus 1 greater than or equal to 0. Getting rid of the parentheses and resolving the numerator, we will have x minus 1 over x plus 1. Now, looking at the rational expression on the left-hand side, a positive 1 will make the rational expression 0, while a negative 1 will make the rational expression undefined. Therefore, in the number line, we're going to mark negative 1 and positive 1. Negative 1, we use a hollow circle because negative 1 will make the rational expression undefined, and a shaded circle for positive 1 because it will make the rational expression 0, which is valid, and that includes 1 in the solution set. Now, negative 1 and positive 1 divides the number line into 3 intervals. What are these intervals? Negative infinity to negative 1, from negative 1 to positive 1, and positive 1 to positive infinity. And then the rule says we are to find a test point from each of these intervals. We can choose the most convenient test point. Between negative infinity and negative 1, we'll choose negative 2. Between a negative and a positive value, the most convenient test point to choose is 0. And between positive 1 and positive infinity, we'll choose positive 2. Then we'll get the factors in the numerator and denominator of our rational expression. We have x minus 1. So we're going to get the signs of the expressions in each of the interval by substituting the test point to the expression. So negative 2 minus 1, that is a negative value. 0 minus 1, negative. 2 minus 1 is positive. The other expression is in the denominator, x plus 1. So at negative 2, in the interval negative infinity to negative 1, that will be negative because negative 2 plus 1 is negative 1. At negative 1 to 1, that is positive because 0 plus 1 is positive 1. And then at 1 until positive infinity, that is positive because 2 plus 1 is positive 3. So we will now get the signs for our rational expression x minus 1 over x plus 1. In the interval negative infinity to negative 1, that will be positive. Negative over negative is positive. In the interval -1 to 1, that will be negative, because negative over positive is negative. And then in the interval 1 to positive infinity, the expression will be positive. That's positive over positive is positive. So the signs of the rational expression gives us the solution to the rational inequality. And since our inequality is greater than or equal to 0, we will get the positive signs as the solution, or the interval with the positive signs as the solution. And what are these intervals? Negative infinity to -1 union 1 to positive infinity. 1 is included, that is a closed interval. In set builder notation, this is all x element of real numbers such that x is less than -1 or x is greater than or equal to 1. Next, let us have example number 2. Solve for x in the inequality 3 over x minus 2 is less than 1 over x. Subtracting 1 over x from both sides so that the right hand side of the inequality is 0. 3 over x minus 2 minus 1 over x is less than 0. Let us combine the two rational expression. So our LCD is x times x minus 2 divided by x minus 2, then multiplied by 3. So we have 3x minus the LCD divided by x times -1. So we have minus quantity x minus 2. Getting rid of the parentheses in the numerator, we have 3x minus x plus 2 all over x times x minus 2 less than 0. So 3x minus x is 2x. So we have 2x plus 2 over x times x minus 2 is less than 0. The numerator can still be factored as 2 times quantity x plus 1 all over x times x minus 2 is less than 0. In the numerator, -1 will make the rational expression equal to 0, while x equals 0 or x equals 2 will make the rational expression undefined. Therefore, in the number line, we'll have -1, 0, and 2. That divides the number line into 4 intervals, which are negative infinity, -1, -1, 0, 0, 2, and 2 positive infinity. So let us have our test points. At negative infinity, -1 will have -2. -1, 0 will have -0.5. And at interval 0, 2 will have a test point 1. And at interval 2, positive infinity will have 3. So our expressions in the rational inequality, in the numerator, we have 2 times x plus 1. At interval negative infinity, -1, 2 times x plus 1 is negative, using the test point -2. At test point -0.5, this is positive. And at test point 1, this is positive. Also at test point 3, positive. The next expression is at the denominator, which is x. So the signs of the test points will be the signs of x. Negative, negative, positive, positive. Another one, we have x minus 2. So at interval negative infinity, -1, x minus 2 will be negative. And at interval -1, 0, x minus 2 is negative. At interval 0, 2, x minus 2 is negative. And at interval 2, positive infinity, using test point 3, x minus 2 is positive. Then our rational expression will have the signs negative, positive, negative, positive. And this shows our solution to the rational inequality, since the inequality is less than 0, so we'll have the solution for which the rational expression is negative. So our solution is at interval negative infinity, negative 1, union 0, 2. Written in set builder, it will be all x element of real numbers such that x is less than negative 1 or x is greater than 0 but less than 2. Next, let's proceed to example number 3. Solve for x in the inequality 8 minus x over x squared minus 1 is less than x. Subtract x from both sides so that the right side of the inequality is 0. Then we have 8 minus x over x squared minus 1 minus x is less than 0. The denominator is x minus 1 times x plus 1, and that will be our LCD. So in the numerator, we'll have 8 minus x cubed plus x. The numerator can be simplified as 8 minus x cubed all over x minus 1 times x plus 1 is less than 0. The numerator is the difference of 2 cubes, so it can be factored as 2 minus x times 4 plus 2x plus x squared all over x minus 1 times x plus 1 is less than 0. Notice that in the rational expression, 2 will make the rational expression 0. Positive 1 and negative 1 will make the rational expression undefined, so that in the number line we'll have negative 1, 1, and positive 2. That divides the number line into 4 intervals, which are negative infinity, negative 1, negative 1, 1, 1, 2, and 2 positive infinity. Let us choose our test points. At negative infinity, negative 1 will have negative 2, negative 1, 1, that's 0, 1, 2 will have test point 1.5, and 3 at 2 positive infinity. In the numerator, we have 4 plus 2x plus x squared. Notice that any value will have 4 plus 2x plus x squared positive. Next, we have 2 minus x at interval negative infinity, negative 1. This is positive. At negative 1, 1 using 0 as the test point, this is positive. At 1, 2 using 1.5, this is positive. And then at 2 positive infinity using 3 as a test point, this is negative. And then in the denominator, we have x minus 1. Using test point negative 2, this is negative. Test point 0, this is negative. And at test point 1.5, this is positive. Also at test point 3, this is positive. Then our last expression in the denominator, x plus 1. At test point 2, this is negative. At test point 0, positive. At test point 1.5, positive. Also at test point 3, this is positive. Then what will be the signs for our rational expression? At interval negative infinity, negative 1, this will be positive. At interval negative 1, 1, this will be negative. And then positive at interval 1, 2. So this is negative at interval 2, positive infinity. Since the rational inequality is less than 0, we'll have the interval for which the rational expression has negative sign. Therefore, the solution is the interval negative 1, 1 union to positive infinity. And in set builder notation, this is x element of real numbers such that x is greater than negative 1 but less than 1, or x is greater than 2. That is all. For exercises on this topic, you may download the worksheet at the link given in the description for this video. Thank you for watching. Please subscribe for more math lessons.